All right, well, first off, I'm going to welcome everyone to the Long Coffee Break. This is a weekly series that we are presenting on a variety of different topics. Please do look forward to further topics. Next week, we'll actually be discussing cook and fan controls. We'll talk a little bit about that towards the end of this session. But you can sign up via our invite for these Zoom meetings, and we'll try and keep this conversation to about 15 minutes. I want to let everyone know that this is a recorded line. We'll post this to YouTube afterwards. So feel free to review that if you need to in the future, or send that to colleagues or clients that you feel might benefit from this content as well. Please hold all your questions until the end of the session. If you do have a question, don't hesitate to type it into the chat area. We'll then catalog those and be able to go over that at the end of the session. And when we're finished with those, we'll open up the phone lines if you want to have a direct conversation with Matt or myself about something particularly important to you or a project you might be working on. So at this point, I'd like to introduce Matt Pemberton. He is the regional manager with Dadanco. Thank you, Matt, for joining us today. He's going to be doing the heavy lifting on the presentation that you're about to witness. And Matt, whenever you're ready, you may proceed.
Okay, perfect. So if you can hear me and see my screen and also my mouse, that's what we'll be using for this presentation. So as we discussed kind of previously here, chilled beams are the topic. And the two goals I have in this 15-minute time span is to just discuss what applications might possibly be applicable to use chilled beams. And secondly, why would I select chilled beams for an application layout at all whatsoever? So that's kind of the two goals of the 15-minute time span. First few slides just give you some examples of what chill beams look like in the ceiling. There are many more beams in the ceiling than there should be. This is kind of a showcase room, but laboratories are a great example of an application that we use chill beams and have been for 10 to, you could almost say 15, at least 10 to 15 years. Reason why, one of the advantages of using chill beam systems in a laboratory are laboratories have high sensible load requirements. Chill beams help handle that additional sensible load, and high air change rate requirements. So going back, did a lot of work on the Eastern Seaboard. A lot of university laboratories would have a lot of chilled beams for that. So it's a good application. We're certainly seeing more in hospital and healthcare, and specifically inside patient rooms. Reason for that is changes to ASHRAE 170 code has now allowed us to use hydronic coil style systems in patient areas if they are designed to be sensible only. And even though we do have chill beams with drain pans, we even sometimes might pipe the condensate. A large majority of all the projects we're working on are sensible only cooling. So we're talking about a dry coil. So that's what has now allowed us to move into the hospital and the specifically patient room area of doing dry coils inside those zones. Dormitories are kind of single and dual occupancy rooms. Another good example of opportunity to use a chill beam or hydronic device. And you'll see there's two different chill beams here. There's one in the ceiling that's showing you an opportunity to, instead of, like I had in this screen, these are 2 feet wide by 2, 4, 6, 8, 10 foot long. Sometimes you have the opportunity to take the chill beam, turn it vertical, put it in the plenum. And so below you just have a linear vane diffuser, right? So now you have an 8-inch wide device. So a different ceiling aspect, different aesthetics to the ceiling. And if you grabbed any manufacturer's catalog and were flipping through it, you would notice that there are 5 to 12, depending on the manufacturer, different types of chill beams. And the reason why there's different types is because there are different ceiling types. We put them in drop ceilings, we put them in hard lid ceilings, we put them in bulkheads. All these different applications allow us to still use induction style chill beam systems and still use it with all the different types of ceilings. So along the floor here, you will also see perimeter induction unit, which is really just a chill beam that's now by the floor instead of the ceiling. And those perimeter induction systems have been around for 40, 50 years in older government high-rise buildings, so we're all kind of familiar with those. We don't see too many new designs with this style system, but if you're familiar with those, the chill beam is simply the exact same component as opposed to being along the perimeter, is stuck up in the ceiling. Classrooms. So if we took all of the projects we work on in a year and said what 2 applications are the largest number of applications of layouts we do, that would certainly be education and office. So we spend a lot of time in the education arena designing K through 12 and a lot of university style work. So you'll see here in this application chilled beams along the center of the space down through, not a typical classroom layout, The only reason is there's a couple different systems in the ceiling, but just to kind of point out the chill beams there. But the fact classrooms are, I would say, one of the larger arenas we do. Offices, here's a good example of a conference room. You'll see the chill beam down the ring, down the center of the space here. The reason we kind of talk about this conference room application is typically chill beams are a constant volume system. So when we talk about laying out an office, there's going to be that corner boardroom, that corner conference room that's going to have a high sensible load, high occupancy, but then no occupancy. Say a conference room may get 1 hour of occupancy a day. And so we want to variable air volume control that space. How do you do that when you're implementing a constant volume chill beam style system? So the question is, can you VAV control a chill beam system? The answer is yes. And so that's kind of the purpose of pointing out this conference room area. Normal office space, open office, you'll notice there's chill beams along the center of the space besides the lighting there. What you can't see very well are there's some along the window. Don't necessarily have to be placed that close to the window, just this design decided to do that. But that would tell me that this is certainly a heating and cooling situation because the beams are so close to the exterior, your biggest heat loss being that exterior wall. So those are good examples and applications of where you might find a chill beam system. And then the second question comes, well, why would I choose a chill beam system? It is typically an energy discussion. Sometimes we have chill beams on jobs because they make sense. A good example would be an older historical building with low ceilings or an application with low plenums, very small plenums. The reason that might lend itself to a chill beam is because chill beams are very small in height. The standard chill beam is about 10.5 inches tall. So inside of a plenum and inside 10.5 inches, you can get all your heating, all your cooling, and all your ventilation. So every now and again, we'll see an application that has chill beams just because they needed the plenum space. So they needed a very small component. Sometimes we see chill beams used because they're very quiet. So libraries, courtrooms, we've done a few of those recently, just, have chill beams inside the judicial chamber, inside the jury deliberation rooms. Not necessarily in the courtroom, only because typically the courtroom ceilings are too tall. But again, chill beams were selected because they are so quiet. But typically, it's an energy discussion of transferring, instead of doing all air systems, we're going to do some hydronic heating and cooling. That's really the benefit of why I would choose a beam for energy impacts. Some US GBC numbers here just show you that energy consumption across the US as a whole, the largest portion of that comes from buildings. And then once you break that down, electrical consumption, you'll see buildings are the largest consumer of electrical in the US. So if we can have an impact on that, reduce the amount of energy we're using, that'd be a great thing. How do we achieve that? Again, we're going to trade doing all of our cooling with air and now doing cooling and heating, and now doing that with water. And this little slide here kind of references just the fact that, if you would like to get a ton of cooling, you would need 550 CFM for a rough example. You can get that same amount of cooling inside of water with 3/4 inch pipe and 4 GPM of water. So as we know, the cooling and heating properties of water much times greater than air. So what we're doing in essence is we're going to reduce the CFM we're sending into the space. So we're going to reduce our fan horsepower consumption, but we're going to take care of that heating and cooling hydronically inside the space by the chill beam product. So when we talk about side benefits of chill beams, you're going to help people talk about the fact they're quiet, they very low in maintenance. There's no fan, no filter, no moving parts. Every 2 to 3 years, you're vacuuming a dry coil. That's the maintenance on the beam. So all these side benefits, the fact, again, low in height. The biggest benefit by far is the total fan horsepower reduction. Say, look at life cycle cost analysis of a building. The amount of reduction you're able to take on primary air results in huge fan horsepower consumption savings. So that's really the end goal and big benefit. So active chill beams. I pass right by passive beams because we very rarely use them. Generally, we're doing active chill beams. So how does an active chill beam work? Works just like this. You'll see it's showing here on the top left, 1 part primary air, round numbers, 10 CFM per person, and 10 people in the space. We need 100 CFM of ventilation air. That's the ventilation air that's going to come into the chill beam plenum, pressurize, and it's going to leave with a high pressure and velocity through these nozzles shown on each side. So the primary air exits the chill beam, and what happens with our primary air pressure and velocity, we create a negative area, a negative pressure area behind this coil, and that's how we create induction without any additional fan horsepower. So you'll notice this slide mentions the fact there's 1 part primary air, and the bottom in red, it says 3 to 4 parts of room air. That simply means you're going to induce 3 to 4 times the amount of air as you introduce as primary air. So for our easy round number example, 100 CFM ventilation air induces 300 or 400 from the space. Combine 100 with 300 or 400, and you get 400 to 500 CFM of conditioned air going into the zone. Key is only 100 CFM of that came from a fan-powered dedicated outdoor air system generally. So that's the big benefit. We're now doing localized in the space, hydronic heating and cooling with the chill beam and not doing it with all air. And that's how it's achieved. So as I mentioned earlier, if you grabbed any manufacturer's catalog and flip through it, you'd see many different models of chill beams. They all use this exact same principle for induction and delivery of air into the zone. It's just there's many different models for all the different ceiling types we're trying to put chill beams in. Another key is noticing that the discharge is going lateral. As we leave the chill beam, it's going lateral. And the purpose of that is to achieve good air distribution. Another side benefit of chill beams is the fact there's great air distribution throughout the space. And so air rises, is drawn into the beam, then distributes out into the zone. So good air distribution, floor to ceiling, wall to wall, big benefit. We talked about low maintenance. Again, this says every 4 years. I recommend 2 to 3, but sometimes people go further than that. It's a dry coil, so it's very easy. Again, no fan, no filter, no moving parts, drop down an access panel, and there's your coil to clean. So a couple slides I want to go through just quickly. It's important to understand what might favor chill beams and what would not favor chill beams. So a beneficial layout for chill beams might be one with a moderate to high sensible load. We talked about space constraints, low plenums, talked about the acoustical environment, quiet, the library, the judicial chambers, and then laboratory. And also lead. There's a lot of points to be gained in lead projects with using a hydronic chill beam system. So once we understand those things favor chill beams, it's also very important to understand opportunities where we just wouldn't promote or use chill beams. And not that we would not do a job with operable windows. We certainly might look at leaky construction and really not decide to do it there. But we do have plenty of examples of installations with operable windows. And the key there is understanding infiltration and understanding when windows are open, what the building automation systems control sequences do. And so not that we don't do operable windows, we just like to have additional discussions of how we're going to control our building. But if we see situations where you have a low sensible load or low sensible heat ratios, chill beams won't provide you much benefit. They become expensive diffusers. So we would say choose a different system. If you have high air filtration rates or high latent loads. So areas where you see high latent loads, you typically won't see chill beams because you're going to send so much air to the zone to take care of your dehumidification requirements that you're going to take care of all the sensible load at the same time, and the valve at the beam will never open. So again, another expensive diffuser situation, which we help you avoid. So those are the things that are less favorable. And to kind of wrap up here in the last couple of minutes, just to give you examples of different types and styles, because we talked about different ceiling types. This is the basic go-to standard model for every chill beam manufacturer there is. It's two-way air distribution. You can see the gap here on this side, which you can't see. There's the same gap on the other side. That's where our primary air and our induced air is being delivered into the zone. So this is a 2 foot wide by 2, 4, 6, 8, maximum of 10 foot long, two-way distribution chill beam. Sometimes we might have a smaller area that this is the exact same style unit. You know, we're still inducing air through that perforated panel on the bottom and distributing it out both sides of the chill beam, but this is now only 12 inches wide. So sometimes you may have an application where you have a small foyer area, a small hallway. Maybe you want to put these all along the perimeter and make them one-way air distribution. You'll notice the second line down here at the bottom says two-way discharge or one-way discharge. One-way discharge simply meaning you're distributing air out of only one side of the unit. So for typical, maybe up against a wall type layout, this is the first beam you're ever seeing that has a drain connection. So we're typically doing sensible only cooling, no condensation, but people are concerned, hey, if it does condense, it'll drop in the drain pan. We'll put a water bug in there. It'll click the BAS to say, hey, you got water in the drain pan, go check out what's going on. We won't pipe that, and no need to put condensate pumps or anything in. Very small unit. If this is only 7 inches tall, so if you have a very small plenum, four-way air distribution, all these things are the same as far as induction properties go. And then a vertical coil unit. This is the one that is behind that linear vane diffuser we were talking about earlier, where we've taken the coil and now turned it vertical, and we kind of put it up in the plenum, if we want different aesthetics for our ceiling. This is a bulkhead system. So you can see here the coil is now at the bottom. All of this is buried behind the bulkhead, and all you're going to see is that linear vane supply diffuser sending air out into the zone. And that's my 15 minutes. Thank you guys very much.
Well, thanks again, Matt. Again, next week we'll be talking about Lauren Cook, so please join us for fan controls with Lauren Cook. But to start the question and answer session, I'm often asked about active versus passive beams. I would understand, or I would guess, Matt, that active beams are going to be much higher BTU content, conditioning both heating and cooling. Is that right?
Very true. So, and if we use passive beams, and if I can show you if everybody understands what a passive beam looks like, that picture is right here. And so passive beam is cooling only because heat will rise and it works only through convection. There's no induction principle to a passive beam. It's only through convection. And so these are cooling only, and you're exactly right. You're looking at 300 to 400 BTUs per linear foot, possibly. And with an active chill beam, you're looking at 1,000 to 1,250 BTUs per linear foot. And with the active beam, you can do both heating and cooling. So passive beams are typically used in places where you don't need any additional primary air because there's no duct connection here. There's no induction happening. It's all just natural convection and cooling. And very, as you mentioned, maybe 300 BTUs per linear foot on the passive beam.
Now, you talked before about an induction unit and replacements for induction units. You know, a lot of people have seen the chill beam and actually talked about it being an induction unit just by a different name. But the old induction units we've seen in their replacement are often loud, use a lot of static. How has the technology changed to what we see from active chill beams today?
Sure. So here's that picture of that one along the perimeter. And what happens is, as I mentioned, we don't see a lot of new installations designing induction units, but we do see a lot of, and we do a lot of replacements. As you mentioned, the old technology behind that enclosure there in the corner, if you can see it, in the front is a louvered panel where your air is being induced. And on the top is a louvered area where your supply air is coming from, cooling and heating. But the old systems used, the reason we're replacing them, one, they're say 30, 40, 50 years old, but they had a lot of fan horsepower because they ran at very high statics. 1.5 inches, maybe 2 inches of static, kind of high rise government buildings and a lot of college dormitories we're doing replacements for, a lot of old office buildings too. And the key is new systems use newer technology, and basically, you know, coils are coils, copper is copper, but we understand the ability of how to now manufacture those to make them much less fan horsepower and pressure. So the old systems that might have ran at 2 inches of pressure, we're replacing those systems that now run at 3/4 of an inch of pressure. And so the big benefit by far is that, you know, that big, huge dedicated outdoor air system pumping air up and down all the floors at very high statics. We change all that. Instead of running 2 inches of static, we run it at 3/4 of an inch of static. So huge energy and fan horsepower consumption savings.
Well, back to the future. So a question from the field. You mentioned that chilled beams work well in labs, but labs usually require high air changes per hour of filtered air. I wouldn't think that induced air would count as part of the air changes since it's not filtered with each pass through the chilled beam? Question mark?
Yeah, so very true. It's very, so when I say laboratories, I say laboratories and it's kind of it's too broad of a term, right? So it depends on the type of laboratory you're doing and the filtration rate requirements. Some just have air change rates and some have air change rates required with filtration. So to say laboratory is very broad, and I agree with that. I shouldn't, because it wouldn't be used in a pharmaceutical laboratory, right? But a college bio lab is not that big of a deal as far as the filtration rate requirements for those. And so that's where, when I say a lot of our labs, there's a lot of university laboratories, not, you know, sophisticated, say, pharmaceutical type stuff. So I completely agree with you there. It all depends on the filtration rate requirements, laboratories. And that's also true when it comes into the healthcare arena with the hospital room, the patient rooms. Those have air change rate requirements also. And that's changed to say it's not filtrated change requirements as long as you're inducing air from the same space, distributing it back into the same space, meaning we couldn't, you know, return air from 3 different rooms and then supply it back to 3 different rooms. The chill beam is in a zone. It's only drawing air from that zone and returning air to that zone. So it's considered an air change and not a required filtration air change. So I agree with you. The code would have to be reviewed for each individual style specific lab you were doing to see if it allowed for air changes air changes without filtration. Certainly true.
Well, and to augment that answer, there's certain ways that you can set up the systems as well in order to help provide economization of that and then provide that. I've often seen laboratories where you have an area, let's say right in front of the lab hoods themselves, where you've got some high loads. You could use chilled beams, and then with other diffusers throughout the space, laminar filtered diffusers, if you'd like, you can provide neutral air to the space to meet your air change requirements, but still have a ton of energy savings from what you're actually sending to the lab itself. And in general, we look at all these things when we're trying to put the system together, because the amount of air that you're supplying to the beam, the temperature of that air that you're supplying to beam, which helps with any dehumidification load that you have, the chilled water temperature, the hot water temperature, all these have a great effect on what the chilled beam actually produces. And the nice thing that the Dadanco can provide to you is a spreadsheet that is just amazing. In the past, we'd have to rate each one of these individually, and that's been a very arduous and time-consuming effort. Now we basically just cut and paste your loads into a spreadsheet. It actually does all the calculations for you, and then you can optimize them from there. So the selection of these things has become very easy with the design tools we now have available. That's available on the website, and we can also help you through that as we go along. Another question comes in about how does a chilled beam switch between heating and cooling?
So two ways. We either do a 2-pipe system or 4-pipe. And if we're doing 2-pipe with cooling and heating, there's going to be some changeover system. And when you do that, of course, if you have glycol and chilled water, we need it in the hot water also for doing the changeover system. And so that's basic standard 2-pipe changeover, just like we would for any other system, is the same for beams. And then we have the opportunity to go to 4-pipe. And when we go to 4-pipe, the benefit there is you'll notice on this one picture, on the active chill beam, it's showing you 2 rows of coil. There's a 2-row coil, 1 supply, 1 return connection, and there's 8 tubes in each row. So if we were doing cooling, we'd be using all 16 tubes for cooling. Then with the changeover system, we'd use all 16 tubes for heating. If we want to go 4-pipe, we'd take the same coil bundle of 16 tubes and we'd run a 12-tube cooling circuit and then a 4-tube heating circuit. So still equaling 16 tubes. And we keep those completely separate to where there wouldn't be any hot water and chilled water. And so that's how you could do cooling and heating with 4-pipe in the same 2-row coil, going with a 12-tube cooling and a 4-tube heating, or you can do 2-pipe changeover. Either way.
And there are many different ways to make that work and make it economical. We've even seen 6-way valves that have been included in this in order to allow different control schemes. But it's basically, if the switch is made with the control device that you have using this, whether it's a variable valve, pretty uncommon because we'd like to just flow these full, but you can also use a solenoid valve, and that's a cheaper idea. Another way that we've done that before is installed cooling only beams, but then upstream of that on the outdoor air coming into, let's say, 3 or 4 beams, whatever you might zone out to be either that room or that zone, you could put a hot water coil within that ductwork. That way you don't have to run hot water coil to each of the beams themselves. And then to further augment that, especially for the outdoor air, we've used things like the air control valves, which we covered about a week or 2 ago, in order to control the air going to that. Because again, the quantity of air going to these needs to be set up during the time of installation and is very important to how that chilled beam itself acts and the loads that it gives. So all of those devices and different schemes have been worked out in the past, and there might even be more for you to create. But that's the great thing about the active chilled beam technologies. It allows a lot of different palettes, a lot of different setups for your particular needs, wants, desires, cost, and whatnot. So we've done quite a few of them before. Another question from the field. You mentioned that convection would be the primary heat transfer with passive chilled beams. It seems that radiant transfer would also be significant as well? Question mark.
So the problem with passive beams, let me go up and look at them again here, is there's not much radiant to be had because that perforated spot you see on the bottom here is not the coil. It's a perforated panel that air, comes down through. And so when we're doing cooling only, the radiant effect is kind of mitigated or reduced by the fact that there's a coil and then there's a gap and then there is this perforated panel. So there is a tiny, tiny bit, and in the selection software program thing that is accounted for, but it's large majority, not necessarily 95+%, but it's all pretty much convection on the cooling side of things. Where these are typically 10, 12 feet from the floor, just to give you an idea of floor to beam height. It's not necessarily floor to ceiling height because we can have higher ceilings and just pendant style, hang the beams down from wire, whatever you may do in your space, all thread, something that would look nice. But the large majority of the cooling coming from the passive beam is through convection.
Well, and also too, everyone might be quite interested to know that to name a device a radiant whatever, a radiant panel, a radiant heating device, 35% of the heat that comes off of that needs to be radiant. And actually, that's what a good breakoff is, because you can't stop convective forces. And a lot of it has to deal with, if we go back and open up our engineering book, is the Nusselt number, right? The direction basically that you have the radiant mounted. So in the ceiling radiant panels do a pretty good job. We put a insulation behind them to try and drive heat transfer into the space itself. So there's not a lot of chance for convective to happen in that space. There will be some that happens though, and those have a pretty high radiant percentage of their heating value. However, if you go to something like a Runtal panel that's mounted on the wall, especially low, that is set up directly, especially underneath maybe a drafty cold window, for a lot of convective. And you'll see those numbers from a radiant versus convective drop drastically down into the 40s or that 35% number. So even though you may be specifying a radiant panel, depending how you put it, you're not getting a lot of radiant out of it. A lot of the heat coming out of it is going to be convective anyways, which could be beneficiary depending on how you're trying to use that device itself. So hopefully that's answered some of the questions. And lastly, as a question I'm often receive, is filtration on these devices. There's a lot of people from a knee-jerk reaction to say, there's a coil, I need to have a filter. What would you say about that, Matt?
So an ASHRAE 62 will certainly drive you toward, if you're using a coil that is dry as opposed to a coil that is wet. And so we see applications come through that's using 45-degree chilled water, which we don't never see, right? We're typically above space dew point. So if we are designing our spaces to be 75 degrees and 50% relative humidity, that's roughly a 55-degree dew point. We'll see water temperatures at 57 on the entering side of chilled water. So we're above space dew point, we're a dry coil, and that's kind of the difference of comparing the fact that we don't need filtration on a dry coil, but you would, if you followed ASHRAE, every word of ASHRAE, then you would need filtration on wet coils. And so that's the difference. The difference between a wet and a dry coil. A sensible only application is really what we do with all of our overhead ceiling style chilled beams. Yeah,
and to augment that as well, first off, this is in an area where there's not as high dust. If it's in the floor or in that area where the occupied zone is, I would be more concerned with that. But it's certainly that those dust particles would have to rise up through these convective factors to get into the coil to begin with as well. Secondly, the fin spacing on this, in order to promote that movement of air, is pretty wide. So there's less likelihood of anything getting trapped in there. And lastly, they do provide on the perf panels themselves a fold down area where you can go in and actually change that out. This was a big issue to some users, first off, with chilled beams. And they've found out after having these installed for 5 to 10 years, there might be 1 or 2 cycles within that time that they actually have to go in and sweep those out. So it's not a very dusty environment, and it certainly works against the convective ideas that we have set up. So as long as you, again, have a dry coil, which we always want, this is actually augmented in our particular climate because it's so dry in Utah that we rarely have issues there. And then we have other methods to try and control humidity within the space to make sure that these are dry for several reasons. So those problems, while maybe an issue early on, haven't really borne out to be a problem where a filter is necessary. I actually have one particular project where we did install a mesh filter on the inlet of that, and those have since been removed because they found out that, years later that they were completely clean, and why have it in there? You'll gain some capacity back and less maintenance by not having that device there. So, well, at this point, I'll at least close the discussion. We're going to open the phone lines. If anybody would like to talk, just please happen to, please unmute yourself. But Matt, I want to thank you for your time and your expertise today. And I'd urge everyone else on the call to, again, share this through YouTube with the other videos we have there. Please join us next week. And if you do have any particular questions about chilled beams, their applications, or any of the devices that we offer to the market, please don't hesitate to contact your Long salesperson directly. So thanks again. All right. Well, if anybody else wants to unmute themselves, you're more than welcome to ask as many questions as you'd like. We're here as long as you need us. We'll see how many people drop off at this point, Matt.
Yeah, no problem. No problem at all.
How do you like our coffee graphic? I thought that was kind of nice.
Oh yeah, it's good. Yeah, I like how the coffee just keeps smoking.
I know. I wish that were actually the case with my coffee. Not so much.
Right.
So
yeah, that stuff stayed hot for the last hour.
What's that?
I said that coffee's been hot for the last hour.
Yeah, it seems like it. So I don't know if we're going to be getting any direct questions, but just for you, Matt, where do you see the growth happening in chilled beams? Is there a lot of projects being done in Boston right now, or LA, or some place in particular that you see chilled beams as being in vogue?
So as long as I've been kind of in the chill beam market, which has been 10, 12 years, the northeast US is by far the biggest pocket of interest in layouts, for sure. And it's been that way from the beginning. And that's still the trend. And it is, I would say now, it's kind of speckled interest all over the US. You would think there's areas that, as you mentioned, that are lower in humidity and don't have condensation problems, and you would think would be great for radiant or chill beam products that we see none. And then other areas. So the biggest area I've seen chill beam interest, this is true just for every job I bid. And so I'm thinking of every manufacturer laying them out. The Northeast is by far the biggest. Mm-hmm. When you go out west, the biggest areas are Washington State. There's a lot. Oregon, there's a lot. California is hit and miss, not a lot there. Through the Rockies, it's kind of speckled interest here and there. Midwest is very true. The upper Midwest, you'll see some chill beams. The lower Midwest, there's nothing. And so, I happen to live in the middle of Missouri, and I think there's maybe 3 or 4 jobs installed in the state over the last 15 years, and that's it. It's kind of a DX area, not hydronic.
Yep.
And then go to the Southeast U.S. There's not a lot of interest in the Alabama, Louisiana, that area. There will be in the Carolinas, and then once you start hitting those areas, we do see a lot of interest in North Dakota, Minnesota, Wisconsin. There's some in Illinois. For some odd reason, Indiana, we do a bunch of work in Indiana. I don't know why it is, because there's not much in Ohio. And then you start getting east to where it's kind of speckled in everywhere. All big university work.
I think a lot of it is engineers in that particular area that is serving that market, because a lot of engineering is still homegrown, right? I mean, there's some multinationals that we see, or international, or interstate that we see, but for the most part, it's done locally, and there's a market that has to be developed for it, whether they enjoy the technology, they have some background with the technology. And it's nice to know that a lot of the areas that you mentioned, like, I actually worked on a project when I was an engineer in Florida, which had chilled beams on it. So we've been able to be very successful at making that installation work in places, as opposed to Utah, that has a hugely high humidity. Because that's stumbling block number one, that we're going to make it rain inside the space. But that's just not been borne out in areas that are much more difficult to keep it from raining in space, where it should be something I think that's more useful to the engineers here in Utah. So, well, great. I'll close it down for now. If you have any other thoughts, keep in touch. I do appreciate all the support you give us, that you've given us for over the years, and